right, so we're in section 10.2. All right, let's focus, folks. Let's get started. So what we're going to do today is, like I said, is essentially review. We're going to talk about what we learned. We've learned about vectors already. We did a fair amount with vectors. We're just adding our z. We're adding our z coordinates to our vectors. So that's the only difference between what we're talking about today and what we talked about at the beginning of the semester in chapter 6 is our vectors have a z component rather than just the x and the y component. Everything else is exactly the same. So in space, in three dimensions, our component form, and we're just going to kind of go quickly through a lot of these ideas and do examples for just a couple of them. Our component form, we have three components now. So our vector, if our vector is v, our component form is v1, v2, v3. And the little angle brackets mean we were talking about a vector. We can also use our standard unit vector notation. And you see standard unit vector in physics and science a little more? So in standard unit vector form, we say that v equals v1 I hat plus v2 j hat plus v3 k hat, where I hat, j hat, and k hat, I, j, and k are our standard unit vectors. So I hat is our unit vector. Unit vector means its length is 1 in the x direction, so it's 1, 0, 0, points along the x-axis. J hat is our unit vector in the y direction, so 0, 1, 0, so it points along the y-axis. And k hat is our standard unit vector in the z direction, and it's 0, 0, 1, points along the z-axis. So these two forms mean exactly the same thing for this vector. The zero vector. Our zero vector is 0, 0, 0. All three components are 0. And it's important to remember that the zero vector does not equal the number 0. One's a vector, one's a number. They're different things. The vector from between 2 points, the way we find the vector between 2 points, we're going to let's call point 1 P, and its coordinates are P1, P2, P3. And our point Q, and we're going to call that Q1, Q2, Q3 are the coordinates. You remember how we found the vector between points in the plane? Take the final point, the components of the final point, and subtract the components of the initial point. So our vector PQ is going to be the vector Q1 minus P1, Q2 minus P2, and Q3 minus P3. And we can think of this as the final point minus the initial point. So that would be our vector between 2 points, a component form of that vector between those 2 points. And this is exactly what we did with vectors in the plane. We just didn't have this third component. We just had 2 numbers that we had to deal with. Our vectors, we can tell when vectors are equal. Remember how we decided when vectors are equal. What has to be true if vectors are equal? They have to have the same magnitude. They have to have the same direction. How can we easily tell if they have the same magnitude and the same direction? If we have them written out in component form. What's that? No, I think you were, what did you say? You said something like the points match? The components are exactly the same. 2 vectors are equal if their components are equal, if their components are the same. So if we have our vector written out in component form, we just look at the x component, the y component, z component. If they're all the same, then the vectors are equal. That's how we tell the vectors are equal. So saying the points match, that's pretty much it. All right, magnitude or length. Kind of going quickly through these things because we've talked about all of these things before. Our magnitude, or we can also talk about the length of our vector v, which we're going to say is in component form v1, v2, v3. Our magnitude, we write this double bar around it. Square root of v1 squared plus v2 squared plus v3 squared. And this is exactly the distance formula. We're just finding the length of the vector, the distance between the endpoints of the vector. Exactly the same as we did in the plane, we just didn't have this third component here. A unit vector. And by unit vector, again, we mean a vector with length 1, or magnitude 1. So a unit vector in the direction of v. Remember how we found a unit vector in the same direction as another vector? Had to do with the magnitude. We take our vector and we divide it by its magnitude. So we're dividing the length out of the vector. So that's how we find a unit vector in the direction of another, in the direction of a vector. If we have u equals the vector u1, u2, u3 in component form, and v is in component form v1, v2, v3. Remember how we found u plus v. Add the components. u1 plus v1, u2 plus v2, and u3 plus v3. So we just add the x components, add the y components, add z components. So to add vectors, we add components. And subtracting is the same, we just subtract the components. And to multiply by a scalar. And the scalar just means a number. So k times u, we multiply each component by the scalar. Yeah, so scalar just means a number. So to a scalar multiple, we call this a scalar multiple. We just multiply each component by a scalar. All right, questions so far? Hopefully some of this starts ringing a bell, starts bringing back some memories of the beginning of the semester. All right, the next thing we're going to talk about is the dot product. Dot product is one way of multiplying vectors. And our dot product, if we have u, our vector u is in component form u1, u2, u3, and v is v1, v2, v3. Our dot product u dot v, we multiply the components and add. We get u1 times v1 plus u2 times v2 plus u3 times v3. So multiply the components and then add. And we also said that another way that we could find the dot product is that u dot v is the magnitude of u times the magnitude of v times the cosine of the angle between them. So we use this formula. In chapter 6 we said that this came from the law of cosines. We use this formula to find the angle between two vectors. So we just divide both sides by the magnitude of u and the magnitude of v, and we say that the cosine of the angle between the vectors is u dot v over the magnitude of u times the magnitude of v. And 0 is less than or equal to theta, less than or equal to pi. So our angle is somewhere between 0 and 180 degrees between these vectors. We also use the dot product to tell if vectors are orthogonal. Do you remember what orthogonal means? Perpendicular, 90-degree angle between them. So we use the word orthogonal to mean there's a 90-degree angle between the vectors. So our vectors are orthogonal, 90 degrees to each other. If, do we remember what's true if our vectors are orthogonal? U dot v equals 0. So our vectors are orthogonal if the dot product is 0. And for this we're saying that u and v are not equal to zero vectors. So because the zero vector, if we take the dot product of the zero vector with any other vector, we always get zero. So we could say that the zero vectors are orthogonal to any vector. So we're saying for this idea, we're saying our vector is not the zero vector. All right, so let's pause here for a second and do a couple of examples. And this should say vectors. Vectors are orthogonal. Orthogonal means they make a 90-degree angle. All right, so let's take a look at a couple of examples using a couple of these ideas. Nothing that we didn't do in Chapter 6, nothing that we haven't worked with before. The only difference here is that we're adding this third component to our vectors. So let's say we want the vector, the component form the vector from the point P, which is 2, negative 4, 1, to point Q, which is at 5, 7, 0, and a unit vector in the same direction. So our component form between 2 points, we just take the components of the final point and subtract the components of the initial point. So PQ, our vector PQ, is going to be the vector, the final point is Q, so 5 minus 2 is 3, 7 minus negative 4 is 11, and 0 minus 1 is negative 1. So our vector PQ would be 3, 11, negative 1. And a unit vector is going to be PQ over the magnitude of PQ. So let's find the magnitude of PQ. Magnitude of vectors is easy. We get the square root of 9 plus 121 plus 1, which gives us the square root of 131. And I'm not going to rationalize my denominator here, so I'm going to say our unit vector in the direction of PQ is the vector 3 over the square root of 131, 11 over the square root of 131, and negative 1 over the square root of 131. So there would be a unit vector in the same direction as vector PQ. So it's in the same direction because these numbers in the numerators are the same, so it's pointing in the same direction. Just dividing each component by the square root of 131 makes sure that our magnitude, we found the magnitude of this vector, we would end up with the magnitude of 1. All right, questions on that example? Okay, let's look at an example with the dot product. Let's find the angle between these two vectors. Between u equals negative 2, 3, 0, and v is 1, negative 5, 1. So we know that our angle theta is going to be the inverse cosine of u dot v over the magnitude of u times the magnitude of v. So we need to find u dot v, and we need to find our magnitudes, and then find the inverse cosine. So u dot v is going to be negative 2, 3, 0, and we're finding the dot product of that with 1, negative 5, 1. So u dot v is going to be 2 times negative 1 is negative 2, 3 times negative 5 is negative 15, and 0 times 1 is, and we're adding, plus 0 times 1 plus 0, so we get negative 17. So that's going to be the numerator here, is negative 17. And then let's find our magnitudes. The magnitude of u is the square root of 4 plus 9, so we get the square root of 13. And the magnitude of v is the square root of 1 plus 25 plus 1. We get the square root of 27. So plugging this into our formula to find our angle, inverse cosine of negative 17 over the square root of 13 times the square root of 17. And I plug this into my calculator, find the inverse cosine of this quantity, and I get that my theta, my angle between these two vectors, is about 155.1 degrees. So we had to find our dot product, multiply the components, and add them. Found our magnitudes. Found the inverse cosine, and we were set. And if u dot v turned out to be 0, we would know that the angle between them is 90 degrees. Questions there? Okay. Couple more things, all we need to talk about. Parallel vectors. You remember how we decided if vectors were parallel? They're good in the same direction between the 2 points. So they had to have so there's an easy way to tell if they go in the same direction. Two vectors are parallel if one is a scalar multiple of the other. So we're saying u equals some scalar times v. So all we're doing is our vectors are parallel. If one is, we can multiply one by some number and get the other. So let's look at a quick example. Are these two vectors parallel? U equals 261 and V equals 1035. Parallel. Are those two parallel? Can we multiply one by some number and get the other one? Did I write my? So this. Oh, yeah, I wanted this to be 30. So the way I wrote it, they were not parallel. How about now? Are they parallel now? Yes. So what's our scalar? 5. So V equals 5 times U. So yes, they are parallel. The way I wrote it before, They would not have been parallel. So that's the easy way to tell if vectors in space are parallel. When we talked about them in the plane, we talked about them having the same slope, but in space, the idea of slope is not quite the same thing. So we have to figure out another way to talk about their direction, and this is how we talk about their direction. Another similar kind of problem, but we have to think about this one a little more, are the points P, which is 1, 3, 4, Q, which is the point 3, 2, 7, and R, which is the point 5, 1, 10, collinear. So first thing we need to figure out is what do we mean by collinear? What are we asking? Are they all on the same line? So this question is asking us, are these points on the same line? Can we draw a line that goes through these points? Co means together, linear line, so together on a line. How are we going to approach this problem? How can we tell if points are on a line? In the plane, it's kind of easy. We could write the equation of the line between 2 points and say if the third point is on that line. Find the direction of the first 2 points. Okay, so we could say the direction of the first 2 points, we're talking about the vector between P and Q. And how do we want to, what would that tell us? What would have to be true? The other vector, a vector from P to Q, has to be in the same direction, has to be parallel to the vector from P to R. So what this question is asking us, is vector PQ parallel to the vector PR? They both start at the same point, so if those vectors are parallel, then the vector from P to Q has to continue on and go through point R as well, because they're starting at the same point. So the only way they can be parallel is if they're on the same line. So let's find PQ. PQ, our vector PQ, final point minus the initial point. So 3 minus 1 is 2, 2 minus 3 is negative 1, and 7 minus 4 is 3. And PR, vector from P to R, is the vector 5 minus 1 is 4, 1 minus 3 is negative 2, and 10 minus 4 is 6. Are those 2 vectors parallel? Yes? Because what's true about those vectors? One's a scalar multiple of the other. I can do 2 times PQ equals PR. So yes, they're parallel. So the points are collinear. So those vectors are parallel, that guarantees us those points are collinear. Questions on that example? Yes?
Could you tell if they're collinear if the difference between them is the same? Like if the difference between Q and R is the same? Because you're adding 2 to the x value between P, Q, and R. And then between P, Q, and R and the y value, you're subtracting 1. So can you tell it that way as well?
So the way that you're thinking about it is kind of the way that we talk about lines in space. So that is That essentially is how we.
It's just a different scale.
Right. So that what you're kind of getting closer to how we talk about lines in space. So yes, that would work. Yeah. All right, one last example, and then we're done. For this example, we know the terminal point of our vector v, and vector v is 1, 3, 5. Is the point Q, which has coordinates 2, 5, 8. We want to know what is the initial point. And we can call the initial point P. So how are we going to solve this one? I'll get us started. I'm going to call this P1, P2, P3 for our coordinates. You're on the right track. So what do we do to find the component form of the vector between 2 points? Subtract the terminal points, and then that has to equal our vector. So to find our component form of our vector, we subtract we do the terminal point minus the initial point, the components of the terminal points minus the component of the initial point. So we know that P1, so our terminal point minus our initial point, so 2 minus P1. Our vector has to be 2 minus P1, 5 minus P2, and 8 minus P3. Terminal point minus the initial point, the components of the terminal point, that has to equal our vector, 1, 3, 5. So P1 has to be what? 1. P2 has to be 2. And P3 has to equal 3. So our initial point is the point 1, 2, 3. So just a few operations with vectors in 3 dimensions. What we're going to do on block day is talk about the cross product. Cross product is another way, other than the dot product, to multiply vectors. And we can do some interesting and useful things with cross products. Okay. Homework. There we go.